Hi everyone, welcome to another video for research design and analysis. In today's video, we'll be building on what we talked about with simple regression, where we were taking one continuous variable and regressing it onto another continuous variable, to a situation where we now have a categorical predictor variable. So again, in our previous videos, we've looked at the relationship between continuous predictor variables as the x's and continuous outcome variables as the y. Now we're going to shift our focus to categorical predictors on the x-axis and continuous outcome variables on the y-axis. So, our outcome variable stays the same. It has to be continuous, interval ratio type data. But now we can deal with categorical factors that are qualitatively different, right? So this can be categorical predictors might be things that are natural groupings. So for instance, in cohort studies, you might have one group who were smokers and one group who were non-smokers. Or they could be, in experimental studies, people you have randomly assigned to different groups. So these are groups that are qualitatively different, but we need to be able to assign a numeric value to them in order to set up a prediction and regression equation just like we did in the past. So one word of caution here too, that we can actually create categorical variables out of things that are continuous. So for instance, you might have a measure of anxiety, and you'll have some people who have high anxiety and some people who have low anxiety and everything in between. And strictly speaking, you can take that continuous variable and split it apart. Like for instance, you could start at the median and then say, okay, well, we'll chop it into the high anxiety group and the low anxiety group. And while technically it is mathematically possible to do that, the thing I want to caution you about is that it's usually not a good idea to take a continuous variable and break it into categorical levels. There are situations where that might be okay, but by and large, it's actually going to kind of hurt things from a statistical standpoint. And we'll get into reasons for that a little further along. But for right now, I think the main thing to understand is we want to be thinking about situations where our data come to us in some form of grouping, right? So there is a categorical distinction already. People come in as smokers and non-smokers, or we randomly assign them to the treatment group or the control group. If it comes in as a continuous variable, we probably want to keep it as a continuous variable and use a simple regression model rather than splitting it apart into categories. So as an example of regression with a categorical predictor, let's think about an SAT prep course. So here I've got 20 hypothetical students who either took my ACT prep course or they did not take the SAT prep course. And you can see their actual SAT scores here. And then here are the same data just as a scatter plot with a regression line drawn through there where we have your SAT scores on the y-axis, and then if you didn't take the course or if you did take the course on the x-axis. And, kind of giving away what we're going to discuss, you can draw a regression line through these data and say, what is the best fit line that then will help us determine if there was an effect of taking my course, and is the slope of this line reliably different from zero? So this is exactly the same as what we've been doing with simple regression, right? We want to know, is the slope that we observe in the sample statistically different from zero, which in this case would indicate that there was some effect of taking my course. But the tricky thing now is there's no inherent numeric value to give to no course and no inherent numeric value to give to course. I can't plug words into math, right, and just make it work. So how do I actually do this? How do I represent these qualitative differences in a regression formula? Well, the answer is that it's going to be really the same as what we did before. We just have to pick a correspondence between the levels of our variable, right, course and no course, and some numeric value of x. But once we do that, then it's really the same as the simple regression models we looked at before. We'll have some null hypothesis where we assume there is no relationship between x and y. And then we'll get an estimate of that slope in our data. And then we're going to be interested in, is that slope statistically interesting, assuming the null hypothesis was true, right? What is the slope? That is to say, is the effect of taking this course statistically different from zero? So in order to do that, we have to come up with numeric codes to represent our categorical variable. And there's a few different strategies for how you might want to do that. I'm going to switch to an example with smokers and non-smokers for a second, just because I have like a little smaller data set here with unequal numbers. But the first way we can do this is by creating what's known as a contrast code. And in a contrast code, you are going to pick values that when added together equals 0. So the sum of the lambdas, and the lambdas are our code, and k is the level of the lambdas, is equal to 0. So for x1, right, the sum of the code number 1 is equal to 0, right? I have a +1 and a -1. If I add those two things together, that's 0. Similarly for x2, I have a +0.5 and a -0.5. If I add those two levels together, that's 0. So these are both contrast codes so far. With code number 3 over here, though, I have 1 and 0. So those sum to 1. So this would not be a contrast code. x1 and x2 represent contrast-coded variables. x3 is not a contrast-coded variable. And again, it's important to remember that this contrast code is determined by the levels of the code, not by the sum of the variable itself, which is a little more apparent if I show you over here. Right? We have one less smoker than non-smoker. So if I actually just add up the rows, right, to get the sum of that variable, the sum of the x's is equal to 1. The sum of the lambdas is equal to 0. And that's what matters from a contrast coding perspective. Right? Similarly for x2, the sum of the x's is 0.5, but the sum of the lambdas is 0. And for x3, like we already said, this isn't a contrast code, but the sum of the x's there is 5, whereas the sum of the lambdas is 1. So again, a contrast code is something that is balanced in terms of how you represent the different levels. It doesn't necessarily have to be balanced in terms of the number of observations in each of your groups. The second code that we have here, though, over here, right, we have x3. x3 is a treatment-coded variable, or what's sometimes known as a dummy-coded variable. And in a treatment code or a dummy code, rather than having levels that balance out and sum to 0, you have one level that is always coded as 0, and that is your reference level, or the dummy, against which the other level is being compared. And we'll look through at an example of this in a second, right? But basically this is, you're coding one level of your variable as 0 the whole time, and you're coding another level as 1 the whole time. But both of these codes, whether it's a contrast code or whether it's a treatment code, are effective methods for coding your categorical variable and then entering it into a regression. And we need to talk about them both because they both have strengths and weaknesses, and different statistics programs will actually code categorical variables in different ways. So you need to know how it's coding your data in order to make sure you can interpret the slopes that you get back out of your stats program. So let's look first at using contrast codes in practice, because I would say those are by far the most common in many areas, and they have some preferable qualities. But let's say that we contrast code our x variable as +1 if you took the course and -1 if you did not take the course. So again, here's our SAT data on the y-axis, and it's the same categorical distinction, but now rather than having a discrete variable on x of you took the course or you didn't take the course, I have a continuous variable, right? It goes from -1 to 1. If you didn't take the course, you get a -1. If you did take the course, you get a +1. So we can now regress these two variables onto each other, right, and calculate a slope. And in much the same way we did with simple regression, we're going to have a null model where we hypothesize there is no effect of the SAT course. From the data, though, we're going to get the slope that we see here, right? So under the null model, we assume in the population there is no relationship between the SAT and the prep course. In the data, we'll get some estimate of the true beta, right, which we can represent either as B, indicating the slope in the sample, or sometimes we might call this beta hat to indicate that it's the predicted beta. But then we can calculate, okay, well, what was the probability of observing a slope that large or larger, assuming that the null hypothesis is true? And if that probability is really small, we would reject the null hypothesis and say, maybe there is a systematic relationship between the SAT and my prep course. So first, let's think about how we're going to do this calculation right under the null model, where we assume that there's no relationship between x and y. So we're predicting our y values, as always, as the outcome, right? And we're going to have some intercept. And in the null model, we assume there is no relationship, right? So the null model assumes that the true value of the slope is 0, which means x times 0 just kind of goes away. And what we're left with then is that if there's no relationship between x and y is best explained by just an intercept, right? A flat line that does not change as a function of x. To find the best fitting intercept, it's pretty easy to do because, as you might recall, the one value that will give us the smallest sum of squared errors for a set of numbers is always the mean. So if I only get to pick one number, which I do here, right, then the mean is going to be the value that gives me the smallest sum of squared errors. I can calculate the mean y pretty easily, and my null model makes a pretty simple prediction, right? For every person, it's just going to predict the mean, then I'll have some amount of error left over. So I'll have my y's, I'll predict 591 for each person, and then I'll have an error for each person, because some people were above that, some people were below that. I can then calculate the squared errors, right, and then get the sum of squared errors. And this will tell me the sum of squared errors in y, which is to say how much variability is there in SAT scores, assuming that there's no relationship with the data. We can then contrast that null model with our error under the alternative model, right? So again, we're going to be estimating our y sub I as a function of beta 0 plus beta 1 times x plus our error term. And in the previous videos, we showed equations for calculating this beta 1 when you have continuous values. And that will still work in this situation to get an estimate of the slope. But one of the nice things with having categorical factors is we can actually take a little bit of a shortcut here in our calculation of the slope. So remember as we've talked about in previous videos, and as I just mentioned on the previous slide, right, if I get to pick one value, the value that gives me the smallest sum of squared errors is the mean. So now I know I have two different groups. So if I want to make the best prediction for each group, we could reason then that the best value to predict for everyone who took the course is the mean of the course group, because that mean value will then give me the smallest sum of squared errors in that group, right? And for people who didn't take the course, I should predict the mean of people who didn't take the course, because that will be the one value that gives me the smallest sum of squared errors in that group. So assuming I don't have any other predictors in my model, right? It's just, did you take the course or not? What will give me the smallest sum of squared errors is if I can predict the mean for one group when you're in that group, and the mean for the other group when you're in the other group. So the easiest way to achieve that and to get a slope that will do that math for us is to take the sum of each contrast code times the mean of y and then divide by the square of the contrast codes. So in this case, right, I can calculate the mean for the no course group, and it's 577. I'll multiply that by the code for the no course group, which is -1. And then I'll add to that the mean of the course group, which was 605, multiplied by the code for the course group, which was 1. And then I'll divide that by -1 squared plus -1 squared, which leaves me with 28 over 2, or 14. Okay, so this difference then, this slope, is 14 points. So that tells me that as I change by 1 unit, right, because remember the slope is always the change in y, the predicted change in y for a 1 unit change in x. So this tells me then that as my x variable changes by 1, my y value goes up by 14 points. And that what you can think then is that when I start out at -1, that's the value for somebody in the no course group. And if I go up by 1, right, I'd be at 0. If I go up by 1 again, now I'm in the course group, because no course is coded as -1, course is coded as +1. So this 14 points indicates then half the difference between my groups, because it takes me 2 points to get from no course to course. So this slope is really telling us about the mean difference between the two groups. The next thing we need to calculate, though, is what the appropriate intercept is here. And if we have contrast coded our variables, this becomes easy to do again, where we can calculate the appropriate intercept as a function of the sum of the average of each y value in each group divided by the number of groups that there are. So the sum of the y values, the sum of the average SAT score in each group, right, is 605 for the course group plus 577 for the no course group, and then I divide that by 2 because I have 2 groups, and that leaves me with 591. So in my model where I actually make a conditional prediction and I allow my prediction of y to vary based on whether or not you took the course, the best fitting regression model is going to be 591 plus 14 times x. And this will be the best fitting regression model in this situation. So if we contrast coded this, right, as we explained, those are the parameters that we're going to get here. And you could, in fact, kind of plug that in to double check that that fits with this line. Okay, our intercept is the predicted value of y when x is 0. So if I've contrast coded my variables, x is 0 on average between the two groups. So the mean of the group means is going to be 591, which checks out with our regression line. Now, if I go up 1 point, right, away from 0, I'm going to get a 14-point increase, right, and get the mean of the course group, which is 605. Alternatively, if I plug in -1, right, for x and go down 1 point, because -1 is the code for the no course group, now it would be 591 minus 14, which leaves me with 577, which is the mean of the no course group. So I have a regression line then that predicts the mean of each group for everybody in that group. And that's going to give me, in this case, an R-squared value of 0.0196, or about 20% of the variance in SAT scores is explained by whether or not you took my course. We can now contrast that, to make a little pun, with the treatment coding for the same variable. So with treatment coding, again, remember, we're plugging in 0 for one level of x and plugging in 1 for the other level of x. And if I do that, I get very different parameter estimates for my intercept and slope. But the regression line, right, really looks the same. It's just that my x-axis has changed. So if I coded no course as 0 and taking the course as 1, now 0, right, for x isn't on average between the two groups. Now 0 is the no course group. So 577, right, the intercept is the predicted value of y when x is 0. And in this case, x is 0 if you didn't take the course. A 1 point increase then, right, now is taking you from the no course group into the course group. So now the slope is 28. It's double what it was up here. Because in the contrast code, it took us 2 points to get from no course to course. In the treatment code, it now only takes 1 point to get from no course to course. And remember that the slope is always the predicted change in y for a 1 unit change in x. So by changing, what an x equal to 0 means, and by changing what a 1 unit change in x means, right, the contrast codes and the treatment codes will give me different slopes and intercepts, but they will give me the exact same model fit. So the R-squared statistic is exactly the same between these two models, because ultimately, this regression line is reducing the sum of squared errors by the same degree. So once we have those parameters, right, and in practice, we're not going to calculate these things by hand, we're going to get them from a statistical program, right, we can actually make some inferences about their statistical significance, right? Or how likely is it to observe that parameter under the null hypothesis? And we have a few different ways to do that. The first one is that we can actually do a t-test for each parameter. The second one is that we can do an f-test for the model in an analysis of variance, which is what we're going to talk about in the next video. But let's focus on the t-test for now. Recall that we have a generalized formula for getting a t-observed value. We have the actual estimate that we get from our data minus the hypothesized value of that parameter under the null hypothesis divided by the standard error, right? And if we knew all these terms, we could solve for it perfectly, but we have to estimate these things based on what we observe in our sample. So we'll have the slope that we observed in our sample divided by our best estimate of the standard error of the slope. And that will tell us how likely was it to get a slope this large or larger, assuming the null hypothesis is true. Because again, the t-value tells you, how far away from the null prediction were you in units of standard error. So if our effect size goes up, right, and this b value is really big, that's going to make the t-value larger. Or if our sampling variability goes up, that's going to make the denominator bigger and ultimately make the t-value smaller. Okay, so things will be more unlikely if we have very precise estimates, and if we observe very big effect sizes. But ultimately, we can get a t-value for both the intercept and slope in order to calculate a t-test, right? And say, assuming the null hypothesis is true, how likely is it to observe a slope or an intercept this large or larger? So this gets into an interesting distinction between kind of a t-test versus the t-test. And so especially if you've taken an undergraduate statistics course, you might have been taught about the independent samples t-test, right? And that this is a special type of statistical analysis that we use only for comparing two group means. In reality, though, this independent samples t-test is just a special case of the general linear model. The t-test that we do to calculate the difference between two group means is exactly the same as the t-test that we did to calculate the significance of a regression slope when we were dealing with simple regression. So whether our x variable is continuous or whether our x variable is a categorical factor, we can use a t-test to establish if the difference between groups or to establish if the relationship between x and y is statistically unusual given the null hypothesis, right? So if you think about the phrase the independent samples t-test, that's really just a special case of a regression model. We can conduct t-tests for intercepts, we can conduct t-tests for slopes, we can do it when the x variable is continuous, and we can do it when the x variable is categorical, right? And when people say the independent samples t-test, that's the special case that they're usually referring to. We have two independent groups, and we're looking at the difference between those two group means. But the difference between those two group means is really just the slope in a regression model.